Hello, and welcome back to another video on machine learning in biotechnology. My name is Ian Hoffecker, and in this video, I'll be talking about logistic regression. And this is a kind of lead into the topic of neural networks via single layer perceptrons. So the topics I'm going to go over are first a bit of a review of linear regression, which we talked about previously, about the features that one gets from linear regression and how we'll transform these when we start thinking about logistic regression. And we're going to look a bit at correlation between variables and how this relates to the performance of a linear regression model. And then the idea here is that this is sort of the foundation for the topic of logistic regression, which is a type of classifier. So previously, we also talked about classifiers. And this is a kind of classifier version of linear regression. And we'll go over the model, how it's parameterized using maximum likelihood estimation and negative log likelihood, and a quantity called the binary cross entropy. We'll talk about how one performs the optimization in practice using the gradient descent method and the concept of an epoch or an iteration in the training loop. So going back to the idea of linear regression, we talked first about fitting a line. So the concept that's probably most familiar to us from Excel or spreadsheets, you produce a scatter plot and you want to fit a line to it. So you click a few buttons and then you get this line plus an equation, which is y is equal to some slope parameter times x plus some intercept, or y equals mx plus b. And the idea was that it's the same here, except we're potentially adding more variables. So instead of just x, we're also considering the possibility that maybe you have two input variables, x1 and x2, in which case you're not fitting a line anymore. Now you're fitting a plane, where the height then is the y, or the outcome variable that you're interested in predicting. And you again have bias term or an intercept, so a starting value of y, or our outcome variable. And we would typically denote this with W sub B, WB, or W0 here in the machine learning notation conventions. And we have these feature terms here. So one for each input variable that we have. So if we have three of those, x1, x2, and x3, these are going to be summed together plus the bias term to give us our outcome variable. And each of these are multiplied with a coefficient here, or a weight, we're going to call it. And this is the same as the slope parameter when you're fitting a single line, but we're calling them weights because this will be related to the concept of weights in neural networks that will come later. And so when you have more inputs, it becomes harder to picture, but the idea is still that we're fitting some kind of hyperplane in multi-dimensional space where we still have a single outcome variable that we're trying to predict from this summation here. And so what makes it linear regression is that we have this linear combination of features which determines our output. And so and then the other important thing here is that this is a continuous output variable. So y can have any value from minus infinity to infinity. And the idea is that our model is going to spit out a number for us, or predict the value that y would have. But maybe we want a classification system. So in contrast to a continuous output variable, maybe we have a class label is our output. And so we previously talked about a type of classifier called the Gaussian mixture model. And in this case, we were fitting a sum of distributions to some data. And the idea was we could turn this into a classifier by attributing data points to one or other of the parent distributions, or the underlying distributions here. And so the result of this setup was that we would sort the data into classes, so apply class labels to them. And so this is a feature of all classification algorithms. So the Gaussian mixture model is an example of a probabilistic classifier. You have also k nearest neighbors, linear classifiers such as the support vector machine. And what we're going to talk about today, the logistic regression, is also a form of a linear classifier. And then neural networks are also frequently going to be used for classification problems. So we'll see those later. And along with classification algorithms, we have metrics to gauge their performance. And so one of the most straightforward methods for metrics here is going to be the accuracy, which is fairly intuitive, but this has the issue that it's insensitive to imbalances in your training data. So for example, if I have a rare event that happens 1 in 1,000 times on average, I could create a classifier that just simply spits out a negative result every time, and it would still be right 99.9% of the time. So in that sense, it has very high accuracy, but if it's always spitting out a negative result, then this is not going to have any predictive capacity. So to look at the actual predictive capacity of our model, we have to start thinking about false positives, false negatives, true positives, true negatives. And we can do this in the context of the confusion matrix, where we're assembling these quantities. And then we can also start thinking about the precision and recall. So these ratios of, so in the case of the precision, we're asking a question out of all positives, how many are true positives? In the case of recall, out of all in that class, how many are true positives? And this becomes a kind of sensitivity metric. And then the F1 score kind of combines these ideas. So it's the mean of the precision and recall. And we can think of this as essentially how many times the model has correctly predicted the result. And so the idea here is to tackle the logistic regression classifier. And it starts out very similar to linear regression. So we're going to start out with this linear combination of features or terms. So a summation of terms where we have our input variables here, x0, x1, x2, and they're multiplied by weights, weight 0, weight 1, weight 2. And we have a term here, weight w sub b, or the bias term, which is again going to be our intercept or starting value. And instead of y here, we have this symbol a, and this is going to represent the logit or pre-activation function, also called log odds. And the idea here is that this linear combination of features, or a, the logit, is going to be an input in this logistic function or sigmoid function here. And so the model that we're using is transforming this, what would be a linear regression, we're transforming it into a binary classifier by using this sigmoid function. And so the sigmoid function is this S-shaped curve here, where you have 0 at the bottom and 1 at the top, and a sharp transition in between. And the idea is to map values of A, of our linear combination of features, map those values to probabilities that the outcome variable is either 0 or 1. So we have two options and then a probability of being one or the other. And so this is what this model here is saying. So we have a conditional probability, and we're interested in this quantity, the probability that y, our outcome variable, is 1, or that the class label is 1 here, given x, our data, and a given set of parameters. And it's going to be equal to this sigmoid function of a, the logit function. And we'll represent the sigmoid function with this Greek letter sigma here. So in practice, it's going to look like this. So we have this pipeline here where we're starting with some data, x. This is our input. It's going to be a matrix where we have different x variables, x0, x1, x2, x3, and so forth. And for each of those, we're going to have a collection of individual data points, which have their own values for each of these x variables. And so one individual data point, like this circled here, is going to correspond to a single outcome. So that's our y vector here. And so these can take on the numbers 1 or 0. And the training process is going to be trying to figure out which of these x0, x1, x2 variables are the most important when it comes to predicting the outcome. So which of these variables contribute the most to the outcome result here. So it might be that x2, if there's a high value for x2, then this is going to strongly increase the chances that y is a 1 here. And it might be that x0, a high value here, means nothing, has very little impact on whether it's 1 or 0. So the key parameters we're trying to find are these weights. And the weights are how much these inputs matter. And so what I've done here is illustrated this more graphically. So we've drawn a little network here where each input variable is represented by a node. And we can imagine those nodes lighting up like they are down here according to their value. So imagine the activation on these nodes is the input data that's going in. And what's going to happen is these input values are going to be summed. So we're going to create a linear combination of these values, each weighted by their corresponding weights. So x0 weighted with w0. So we produce this weighted sum, and that's this quantity here. And of course, that's our logic function. That's a from the previous slide. And so this summation, then it will be transformed into a probability using the sigmoid function. So the sigmoid function maps this logit onto a probability, a number between 0 and 1, where the closer you are to 0, the more certain you are that the class label, the outcome here, is a 0. And the closer it is to 1, the more certain we are the class label is 1, state 0 or state 1. And we can see this in action here being animated. So this is for an already trained logistic regression model. And what's happening is different test data are being entered. So different vectors of x, and then those are combining together to activate or not activate the output node here according to their summation, their weights, you can see with the darkness of the lines here, and their input values. And so the big reveal here is that, in fact, what we've just created is an instance of the simplest type of neural network. So this is an instance of a single layer perceptron. And so this is an idea that was proposed by Frank Rosenblatt here. And the idea is that, so it has the components basically that we've already discussed. So a single layer perceptron or a perceptron is going to have an input layer, this set of X nodes here connected by weights to an output. We have a summation function that's going to go through each of these inputs and weights and combine them. And then that summation result is going to be fed into some activation function. And in the case of logistic regression, it's going to be this sigmoid, but the perceptron is more general. So you could use a different activation function, and that would still be a perceptron. So what we're doing is an instance, a particular version of the perceptron. And then you're going to have an output, a binary classification, 1 or 0, and there will be some kind of training regimen, the learning algorithm. So in our case, for logistic regression, this is going to be gradient descent and maximum likelihood estimation. And then implicit in all of this is there's some threshold. So the output result is a probability, so a number between 0 and 1. And what we might say is that if it's below 0.5, then we classify that result as a 0. If it's above 0.5, we classify it as a 1. Or we could shift this threshold to be more or less sensitive to one state or the other. And so the kind of elegant thing behind all this is the inspiration for this, which was that of a biological neuron. So you have these dendrites making up the nuclear portion of the neuron cell. And these dendrites are actually like the inputs that we have. So there are these nodes here that are accepting signals from external source. And each of those contribute in some way, some more important than others, so with different weights. Those contribute to the probability that the neuron is going to fire a signal along the axon. And so we'll get an output signal back here. And this is equivalent to the output node that we have here. So the summation of these terms getting transformed into an output probability, firing or not firing. And so we want to think about how we do this in practice. And we're going to use gradient descent, like I mentioned, and we're going to use maximum likelihood estimation. And so this has been a theme throughout. So we start always with a probabilistic model, a likelihood expression. So this is always going to have the form that we're interested in the probability of the data given some parameters. So that was the case for this Pascal distribution function, where we were interested in the probability of observing a certain number of trials given parameters R and P. And by fiddling around with R and P, we would maximize this P here, this likelihood, and that would correspond to the best fit. We had the same thing going on for the Gaussian mixture model. We were interested in the probability of observing the data given the parameters, and those parameters being the mean and standard deviation and weights of collection of Gaussian distributions. And again, we want to maximize this P here by changing those parameters systematically. And we would do this using the log of these likelihood expressions for computational reasons. And because we're typically working with minimization, we take the negative log likelihood. And then this minimum value of this, our loss function here, then corresponds to the maximum likelihood set of parameters for our particular data that we're given. So we're going to do the exact same thing here. So once again, we have a probabilistic model, an expression, a likelihood expression of the same form. So we're interested in the probability or the likelihood of observing a class label. So now our output variable that we're interested in modeling is a binary label variable, 1 or 0. We want to know the likelihood of observing that data given the input X data and a particular set of parameters. And we have an equation for it, of course, the sigmoid function with our logit linear combination of features. And this is the likelihood expression. And then what we want is the loss function, which again is going to have the same form. It's the negative log of this likelihood expression. And not showing the math here, but we have a result. So for the sigmoid function, there's going to be this negative log likelihood expression that one could derive if you go through it. And this is sometimes called the binary cross entropy. So this is a very typical loss function for classification problems because it's essentially a measure of the difference between predicted and actual class labels. And so you can see here, right, this sigmoid function of A for a particular data point, A sub I. So that's going to be, again, this linear combination of features for individual I or for data point I. So x0 for I, x1 for I. And again, that's going to produce a probability. And then we're interested in comparing that with the actual label yi here, would be our training data result. And so we want to minimize that function, the NLL or the negative log likelihood. And the way we could do that is by throwing it into a numerical optimizer, which would sample values of the loss function by making small tweaks to the parameter vector. But a more efficient way to do this with less iteration and experimentation needed is to directly compute the gradient. So the gradient is a kind of derivative of the loss function, so a measure of the rate of change of the loss function, and an analytical expression of it would then give us the ability to always find the vector or direction of steepest descent in our parameter space. And if we look kind of into the expression here, we see that there's a difference in terms here. We have our outcome variable, 1 or 0, and we have our probability here. So the sigmoid of our logit function, which is going to have some value between 0 and 1. So if it's 0.99 minus 1 here, that's a small difference. So this is kind of an error, and we're seeking to score basically the difference between the outcome and the prediction. And so that's what's happening here. And what we want is to take steps in this space in this direction of steepest descent. And so we can do this by multiplying this gradient with a step size, also known as the learning rate, alpha here. So if we wanted to update our set of parameters, we would take the original set of parameters, a vector here of different weights, and we would subtract this vector here of steps in that space. So it might be a little bit in the x0 direction, a little more in the x1 direction, a little less in the x2 direction, and so forth. And we'll compute this directly by multiplying this step size or learning rate with the gradient. And so here we can introduce the concept of an epoch. And the idea is that an epoch it's an iteration in the training regimen. So it's one complete pass through all the training data examples. So it starts by going through the model and producing a prediction, and then computing a value for the loss function. So the negative log likelihood that you would then use to compute the gradient, or in our case here, we don't even need to compute the negative log likelihood because we have an expression already for the gradient. So in this case, we skip this and we compute directly the gradient with respect to each parameter in the model. And then we perform an update. So we perform this step here. And then we go back to the beginning, repeat the process. So now we have a new set of parameters. We can make a new set of predictions. And we keep going until the gradient stops changing, until the negative log likelihood is a very low value. And this is going to correspond to our optimal set of parameters, or hopefully the global minimum in this parameter space. And so in addition to taking these steps, we can also introduce another concept, which is the idea of learning rate scheduling. And so rather than using just a fixed learning rate size or step size, what we can do is have an adaptive one that changes throughout the training process. So one way we can do this, a very simple method, is to simply link it to the epoch number or the iteration number. So we can add this additional term here, or make alpha here a function of a maximum learning rate and this epoch term here. So 1 minus whatever epoch number we're on divided by the total number of planned epochs. So if there's 1,000 planned and we're on number 1, then this is a very low value. So 1 minus a small value is going to be close to 1. So at the beginning on epoch 1, we're going to be close to our maximum rate or step size. So we're taking large steps, in other words, in the direction of steepest descent. But then as we get further along at high epoch numbers, so close to 1,000 of 1,000 planned, then we'll be close to a value of 1 here. And then this is going to be close to 0. And then the maximum value here will have been reduced to a very small number. And so this is called learning rate annealing. And the idea is that we want to take large steps at the beginning and small steps towards the end to make finer adjustments. Okay, and then we have this idea of metrics or quality control checks, and we can do an additional check here, which is optimized for, or which is well suited for problems involving thresholds. So we have our data, it's distributed throughout this sigmoidal curve here. And if we've fitted our function, parameterized it well, then we have points labeled as 0 associated with a low probability of being labeled as 1, and points, the 1 label, associated with a high probability of being labeled as 1. But if we wanted to tune the sensitivity, we could, instead of making the call at the 0.5 as our threshold, we could lower or raise this to let more in or lock more out when we're actually making our call based on those probabilities. And how the model performs with regard to where we place this threshold here tells us a lot about how it's actually performing. So what we can do is plot on this axis the true positives and the false positives, and then modulate the threshold here and just look at this ratio of true positives to false positives. And this upper left corner here is going to correspond to the best possible model. So a place where all true positives and there are no false positives. And any line above this diagonal here is going to mean that there's some predictive power of the model. But if it's falling along the diagonal, then that means that it's not predictive, it's random. And then you can kind of think of this point here. So we can imagine this is a point where we've moved the threshold so far that we do catch all the true positives, but at the cost of also generating many false positives. So you want to be closer to this upper left corner if possible. So maybe here on the curve would be the best place to choose your threshold. And then the area under this curve also corresponds to, is also a measure of the model's predictive capability. So that's going to be a number from 0 to 1, and then the closer to 1 it is, the better. The closer to 0.5, the less predictive your model is. And then finally, a note here on the idea of doing nonlinear classification. So as with linear regression, as long as we're linear in the weight terms here, the coefficients or parameters, then it's still linear regression. And this means that you can have a function, a nonlinear function of x, and still perform this. So for example, we could have radially distributed data here that we want to classify. And if we kind of unwrap this, transform this from Cartesian to spherical coordinates, or spherical to Cartesian coordinates, then we could achieve a linear division between these points from what was originally a nonlinear relationship. And so this corresponds to substituting a function of x here and still solving for these weights. The concepts here we can look at in the context of an exercise. So this is building off of the previous exercise where we were looking at gene expression profiles for a number of individuals. So we have 400 genes with different expression levels and several individuals. And those individuals also each have a blood sugar level, and a distribution of different blood sugar levels. And the individuals are also labeled with a class label. So this is where this logistic function is going to come into play here. So we're trying to predict the binary outcome. Do these individuals develop diabetes? And we can see there's clearly a correlation between the blood sugar level and the incidence of diabetes occurring here. So is the red heat map here is telling us the proportion of pathological cases. And what we want is predictor for this based on the gene expression profile and not the blood sugar levels. But before we do that, let's also look again at some of this linear regression data from the last exercise. And what I want to do is to look at the correlations present in the data. So we can use what's called the Pearson correlation coefficient here, which is defined as the covariance between two variables divided by the product of their standard deviations here, or this summation of these two, the product of these two differences, x minus the mean, y minus the y mean, divided by the square roots of the respective variances of the two variables, or the standard deviations here. And if the correlation is 1 or -1, that it indicates a strong positive or negative correlation. And if it's 0 or close to 0, then this means there's no linear correlation. And so this is for linear correlation. This is in contrast to the Spearman correlation coefficient, which can be used for nonlinear monotonic relationships. So any case where you're interested in whether there's unique mapping between two variables, regardless of whether it's linear or nonlinear. And so the first exercise here is to break the data into subsets. So what we're going to do is build a script that performs a correlation check between each gene and the blood sugar levels. So looking at all the individuals for that gene and checking their blood sugar levels and computing a correlation value. And what we want to do is sort the genes into two categories: those that have an absolute value of the correlation, so positive or negative, greater than 0.1, and we would call those correlated genes, and those that are less than 0.1, closer to 0, we would call low correlation genes. And what we want to see is how does our linear regression model perform when trained on these two subsets. So we have a high correlation subset and a low correlation subset. And what does our linear regression predict relative to the ground truth in those cases using those training data sets? And so the second, so this in the code here, the task is to complete this function for computing the Pearson correlation coefficient and returning it at the end here. So the inputs are simply the two variable vectors here. Okay, and then the second part of this exercise was to look at the logistic regression. And what we're interested in is doing a epoch step. So we have an epoch loop, and we have a function for computing the gradient of the negative log likelihood for the sigmoid function. So this has already been completed, and our task is simply to perform the update. So we have a set of parameters, and we want to get a new set of parameters by feeding in the gradient for the negative log likelihood and multiplying this with a step or a learning rate, which is supplied as a user supplied parameter or argument to this function. But in addition to that, we want to set up this learning rate scheduling or learning rate annealing concept. So not just a fixed learning rate here, not just a fixed step size here, but one that is adaptive according to which epoch or which iteration we're on. So it's going to start with a high value or a maximum value of the learning rate, and then get progressively smaller and smaller as the epochs advance. Then the result should be this logit function plotted with the probability on the y-axis here, and the data points plotted along this curve, colored blue or red according to their ground truth. So whether they were a 1 or a 0. And the idea here is this should be separating these 1s and 0s as best as possible. And again, this x-axis corresponds to the logit, right? So that's the result of our training, or the linear combination of features here that we're plotting. And we'll also get an ROC curve here that we can use to evaluate the model's performance. So in this part, if we have a look at the exercise, so here you can see the gradient is set up here. So we have a function that is computing the gradient according to this equation that I showed you. So we have an analytical expression in the case of the negative log likelihood for a sigmoid function and the gradient of that. So we don't need to do that part. Actually, the only task here is to fill in the rest of the code here in this epoch loop. So we're going for each epoch, we're performing an update. And the key task here is to use this gradient function to perform this update step. And then the second problem here is to complete this prediction function. So this is for the fitting or the training. That gives you the theta, that gives you the set of parameters. And then to actually test it, we want to simply run our logistic function with our parameters on a particular set of data. So this would be the test data set if we do the test training split of our data for cross-validation purposes. And so that was the code. And then if we kind of look at the results here, we can see that training the model on all the genes produces this kind of curve where we've got more blue dots on the left here and more red dots on the right. And we can see that while it's not perfectly predictive, they're not perfectly separated, we have an ROC curve that is above the diagonal, which means that there is some predictive capacity here that we're utilizing. And the area under the curve, 0.78, is between 0.5 and 1, which is what we want to see. So if it's 0.5, then it means it's not performing. And we can also look at a precision recall F1 score here and see that it's 0.83, which is better than random. And what's interesting is if we can perform this logistic regression on the blood sugar data. So this is for performing predictions of the pathological status on the basis of all the genes. But what if we try to predict the pathological status on the basis of blood sugar level? So this is the one we visually saw looking at this heat map in the histogram. And we see that indeed, you again get a curve above the diagonal here. We get an area under the curve, 0.75, and we get an accuracy of 0.7. All of these are a little bit worse than our gene-based predictor. So we had an accuracy of 0.74 in that case, an F1 score of 0.83 versus 0.819 here, area under the curve 0.78 versus 0.75. So what is going on here? If we look at those low correlation genes that we fetched in the first part of this example, and we run the logistic regression on that as the training data, we'll see that actually there's a little bit of predictive capability here as well. So we again have a curve that's just a little bit above the diagonal here, with an area under the curve a little bit above 0.5, meaning that some predictive capability is leaking through these low correlation genes. And so the reveal here is that I've actually added this in as a hidden structure in the data. So I've created artificially some genes. This is artificial data. So I've created some genes that are not correlated with blood sugar level, but which nevertheless are weak predictors of the pathological status. And so this means that if we train the model on all the genes, we're going to make use of those genes that are linked to blood sugar, and also those that are not linked to blood sugar, but are still good predictors for the pathological status. And so one might consider these useful genes to know about. So maybe blood sugar is easy to measure. So you might ask, why go through all the trouble of looking at these genes when you can just measure the blood sugar, and that gives you the same information? And so the answer might be, well, you have some genes that have nothing to do with blood sugar level, but that also have some predictive capability. So we're getting a better model in the end this way. Very hypothetical situation. To kind of summarize here, we have logistic regression. So again, this is a linear classifier. We started from this logit term that looks very much like the linear regression. So this summation of features, weights multiplied by their input X values, but then we're transforming this into a probability using the sigmoid function. So mapping these logit values onto a range 0 to 1, and that probability is telling us the probability of the result being a 0 or a 1. So giving us a probability of what binary class it's falling into. And we were then looking at the gradient function. So we had an analytical expression for the gradient that we could then use to perform the parameter fetching steps. And we played with the idea of learning rate annealing and looked at what an update would look like in the context of an epoch, a training epoch. And then we talked about how this logistic regression was actually a particular instance of the simplest type of neural network, or a perceptron. And while a perceptron can use other activation functions, architecturally, it's equivalent to what we've done here. So we're performing a multivariate logistic regression. We can draw it in this format with nodes and edges weighted according to the coefficients in these feature terms. And then finally, we looked at these ROC curves that we can use to quantify and visualize the performance of our model. And we saw that these models are strong at predicting on the basis of many small or weak correlations, but kind of combining them all together. And so this is where a lot of the power of these supervised machine learning comes from, is large data sets and high dimensional data, where maybe a human would have trouble identifying correlation or making a prediction on the basis of one of these. But through the power of the training algorithm, we actually get some predictive capability out in the end. So that's it for this video, and the future topic will be more about neural networks and building on what we've talked about here. So see you then.